Let's look at OpenStack's College Physics, Chapter 22, Problem 55. Figure 2257 shows a long straight wire near a rectangular current loop. What is the direction and magnitude of the total force on the loop? So let's write down our knowns and unknowns. We know that the current 1, I'm going to call this current W for current wire, is 15 amps. We know that the current in the loop, they call it I2, I'm going to call it I sub L for loop, is 30 amps. Then we know that R1 is 7.5 centimeters. And we know that R2 is 17.5 centimeters. And we also have the length of one side here, so I'm going to just call it L, and that is 30.0 centimeters. And we're looking for the magnitude and the direction, so basically the force net on the loop. All right, so why is there a force on the loop? Well, because it is in the proximity of this current, and we know that any current will create a magnetic field around it. So that means that this loop of current is going to be in the magnetic field of wire 1. So what is the direction of the magnetic field? Well, if we place our thumb in the direction of this current and wrap our hand around the current, we end up with a magnetic field that is into the page on this side of the current and out of the page on the other side of the current. So this is the area that we're interested in. I'm just going to draw it here. All right, so that means that this loop is going to be in the magnetic field of that wire. Now, each of these sides of the current will experience a force. We have a long straight wire, so the force on it is going to be I, L times B. Same thing for all of these different sides. So I'm going to write down the force is I, L, B, sine theta, let's just be thorough, where theta is the angle between the direction of the current and the magnetic field, and that is 90 degrees in all these instances. The current is going in this direction, magnetic field is into the page, so then sine theta is just 1. All right, so let's see the directions for the different currents. Remember that to apply the right-hand rule, we have to place our hand in the direction of the current, bend our fingers in the direction of the magnetic field, and that the outstretched thumb will give us the force. So I'll start with the very first wire here. I'm going to have the current in this direction, so I'm going to place my hand in that direction, bend my fingers into the page, and get a force in this direction. So I'll call this force F1. Then I will go around this way, and on this portion of the wire, the current is going to go down, magnetic field is into the page, so I'm going to bend my fingers in that direction, and my thumb will be in that direction. I'll call this F2. Then I will follow the direction of the current, so the current is to the right. I'm going to bend my fingers into the page and have a force pointing in this direction, so I'll call that F3. And around here, the current is up, magnetic field is still into the page, so the force will be to the left. So that's going to be my F4. All right, so let's take them one at a time. F1 is going to be current in the loop times the length of the loop, times magnetic field due to the wire. So that is IL times L. Magnetic field due to the wire is mu naught, current in the wire, divided by 2 pi times the distance times from the wire to this part of the loop, and that is 7.5 centimeters. So I called it R1. So this then will be L mu naught I loop I wire divided by 2 pi R1. So L is 30 centimeters, so that's 0.3 meters. Mu naught is 4 pi times 10 to the negative 7th Tesla meters per amps. IL is 30 amps. IW is 15 amps. And we divide this by 2 pi times R1, which is 0.075 centimeters. And we get 0.36 millinewtons for force 1. Let's look at force 3 next. So that will be the current in the loop times the length of that portion of the wire times the magnetic field due to the wire. And that is IL times the length times magnetic field due to the wire. So that's mu naught I wire divided by 2 pi. And now the distance from the wire to this part of the loop is 7.5 plus 10 centimeters. And I called that already R2. So rearranging this, I end up with L mu naught IL IW divided by 2 pi R2. And you'll notice that the only difference between these two forces is R1 and R2, the separation between the wire and each of these parts of the loop. So when I plug in the numbers, I end up with 0.154 millinewtons. Now for forces 2 and 4, we notice that each part of this wire is a different distance away. So here we looked at the distance that it's away from the wire. But at every single location, this force points to the right and there is a matching force pointing to the left. So if I just basically added over all of these distances here, the forces, the two forces will cancel out. So we'll say F2 and F4 cancel. They're the same in magnitude at every little location, and they're opposite in directions. So then the net force will be F1 plus F3 plus F2 minus F4, I guess. F2 and F4 are equal and opposite. And we end up with 2.06 times 10 to the negative 4 newtons. Millinewtons sounds kind of strange. And since F1 is larger than F3, because it's closer, that means that the net force will be repulsive. So the loop will be repulsed by the current carrying wire.